Alright guys, it's time for first lecture. It's my first time doing this, so bear with me. If you guys remember from before the break, we were talking about centripetal forces and centripetal acceleration. Basically, we're talking about things moving in a circle and what causes those things to move in a circle. So, first we started off with something called the tangential velocity, or VTAN. And we just said, if something is moving with the uniform speed, that means the distance it travels in a circle is just the circumference, which is 2 pi r, and divided by the time that it takes to travel the distance of the circle, which is something called the period, which is just the time for something to make one cycle or one revolution. And then we talked about the centripetal acceleration. And again, we talked about how centripetal means center seeking. So centripetal acceleration is always a center seeking acceleration, and that's what causes things to move in a circle, basically. It causes it to change direction, basically. So the centripetal acceleration was v squared over the radius. And finally, we talked about what causes an acceleration. Well, forces do. So we have the centripetal force, and that just takes the place of the net force, and that's equal to ma, which is now mv squared over the radius. And one thing we did talk about was how centripetal forces are real forces, right? Centripetal forces can take the place. For example, you remember me in class swinging the cork thing attached to a string over my head. In that case, that would be a tension force. That is, that would be the centripetal force. However, some of you might be confused and have said previously in the past that there are such things as centrifugal forces, and that is very wrong. Centrifugal forces, centrifugal means outward seeking, and if there's an outward seeking force of something that is moving in a circle, aka there's a force that's pulling it out of the circle, well, then it's not moving in the circle. Okay, so centrifugal forces do not exist. Everything we're talking about is a centripetal force. Okay. At the end of the last class, I think, or before the break, we were talking about how to use centripetal forces and how to analyze situations of things moving in circles. We did a lab, lab number 9, circular motion, where you had that little the bar that was powered by the motor, and it went around really, really fast. And you guys had to wear eyeglasses to protect your eyes. And a lot of you, and the point of the lab was to use this equation right here, that I'm gonna box, to figure out what the mass of the spinning mass was, and you guys did find that more or less. Now we're gonna talk about actual physical examples of problems that we might be able to solve. So our first problem is something we've done before. So let's do this. The first thing we're going to talk about is things that are moving in horizontal circles. So if you have, for example, you've got a plate, you've got a table here, and something that would be moving horizontally is maybe you have a turntable. I know if you have one of these, maybe they're kind of old-fashioned, so maybe you don't have it. And the turntable has a little arm that drags, needle that drags on the turntable, and it rotates like this. The turntable does. Okay, let's say you have a coin, and you place that coin 30 centimeters from the center of a rotating horizontal turntable. And let's say I tell you that coin at a distance or radius of 30 centimeters, which is 0.3 meters, slips when its speed v is equal to 50 centimeters per second or 0.5 meters per second. So one of the questions I might ask is, well, what is the coefficient of static friction between the coin and the turntable? Well, if you have the coefficient of static friction, well, you're trying to find mu, right? You guys remember friction? You might want to pull out your equation sheet that I've posted on the Haiku page when you're working on anything physics related, because you won't have the equations on the board, so you have to refer to the equation sheets. So you have that equation F equals mu times normal, and we're trying to find that coefficient. And it makes sense that it's the coefficient of static friction that's keeping that coin on the turntable, because, I mean, think about it. Is there any... I'm going to draw a free body diagram of that coin. And this is the x direction. This is the y direction upwards. Is there any... The force is acting in the y direction is a normal force from the turntable, and the weight force of just the force of gravity pulling it down. What's the force that's causing... What direction is the force that is causing that coin to be moving in a circle? Well, at the position it's in right now, it's pointing towards the center of the turntable, which is in that direction. And what is that force? Well, it's not a tension force because there's no string attached to the turntable. It's not a normal force. There's nothing pushing it into the circle. There's no... It's not the weight force. Gravity isn't pulling it towards the center of the circle. So the only force left is the force of friction. So this becomes fairly simple. What we do after we have a free body diagram, if you remember from the forces unit, is we basically just go to F equals ma. And in this case, the centripetal force is just the force that's causing it to move in a circle, or in this case, it's just in the x direction. So if we look at the force in the x direction, we know that we're totally looking at the centripetal force. And we know Fc is equal to mv squared over r. We know the forces acting in the x direction is just the friction force. So we just have the friction force. That's equal to mv squared over r. Our goal is to try to find what mu is. So find mu. So let's replace F with mu times the normal force. And that's equal to mv squared over r. Okay. In the y direction, we don't know what the normal force is yet. Well, we kind of do, because in this case, the normal force balances out with the weight force. So we know that the normal minus the weight force is equal to 0. So we end up with the normal force equaling the weight force, which is mass times g. The mass is actually, we don't know. So if we don't know the mass, then must cancel out somewhere. Mu times, we know the normal force is equal to mg. Oops. We substitute mg for the normal force. Mu times mg is equal to mv squared over the radius. The masses cancel out, and you end up with mu times g, which is 10, is equal to the velocity, which is 0.5 squared, over the radius, which is 0.3. You do that out, and you get give me a second. You get that doesn't make sense. That's divided by is 0.083, which is very low coefficient of friction. Now, what did you notice was the direction for this friction force? We said this was positive, And we also said this acceleration was positive. So, hey, but we're pointing towards the left. So there are actually two different ways you can look at circular motion and look at the directions in circular motion. You could look at it as normal. So like in this case, the friction will be negative. But what direction is the acceleration? Well, that should also, if the force is negative, well, the thing is also accelerating in the negative direction, so you have to account for that. And if you notice, if you make both of these negative, well, they'll both cancel out. So it doesn't really matter. Another thing to think about, another way to describe directions in circular motion is, if you have a circle, everything that points toward the center of the circle is positive, and everything that points outside the circle is negative. That's another way to do it, and that's the way I would recommend you guys do it. So note, any vector that points into the circle is positive. Any vector yada 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 is negative. The points out of the circle is negative. Okay, so this combined with our problem-solving steps from the forces unit is how we're going to solve any question that relates to horizontal circles. And horizontal circles are relatively easy because you don't have to worry about the force of gravity. Our next video will be talking about vertical circles, in which you will have to take into account the force of gravity. Okay, so that's one example. Best of luck, and if you have any questions, you can schedule an appointment with me after one during my office hours. Okay, all right, see you guys.